Hi, I'm Mipai from Levy Group at University of Pittsburgh and Pittsburgh Quantum Institute. Today I'm recording this offline video because unfortunately our APS 2020 Denver is cancelled due to the fear of the spread of coronavirus. And the talk is about superconductivity in 1D zigzag nanowires at length eliminate strong-10 titanate interface. So the superconductivity of strong-10 titanate is first reported by Scully and co-workers in the 60s. It was the very first superconducting semiconductor at carrier concentration as low as 10 to the 18th per centimeter cubed. Even though that the superconducting critical temperature, the TC for strong-10 titanate, is merely 200, 300, sometimes 400 millikelvins, the superconductivity of strong-10 titanate is similar to that of a high-TC superconductor in many ways. For example, strong-10 titanate superconductivity has a dome. That's the superconducting transition temperature as a function of the carrier concentration, traces a dome, just like this data taken by Kunz and co-workers in the 60s. A pseudo-gap phase for strong-10 titanate has been reported. A small Fermi surface for strong-10 titanate, thanks to its small carrier concentration. Vicinity to additional quantum phase transition. And very importantly, unknown pairing mechanism. So over the past 5 decades, that a lot of pairing glues has been proposed for the strong-10 titanate. And usually people try to think of a mode or a combination of modes that can glue two electrons together, the electrons at the antipolar position on the Fermi surface. And as you can see that there are still ongoing debates between, for example, Alex and Jonathan. On the other hand, the interest in the superconductivity for strong-10 titanate has been really refueled in the last decade due to the discovery of the two-dimensional electron system at the interface between length illuminate and undoped strong-10 titanate. The two-dimensional electron system can exist whenever the thickness of the length illuminate layer is thicker than 300 cells. The 2D electron system resides on the strong-10 titanate side of the interface and inherits a lot of properties from strong-10 titanate. But now these properties can be very effectively tuned by electric field effect from, for example, superconductivity to ferromagnetism. So the two-dimensional electron system, at least in the interface, can be tuned between conductive and insulating globally by gauge voltages and locally by conductive lithography. So to do that, you grow 3 unit cells of length illuminate just below the critical thickness for the two-dimensional electron system to exist. And then you bring a atomic force microscope probe to the sample, you apply a positive bias voltage. This voltage dissociates the water molecules in the atmosphere and deposits protons onto the top surface of length illuminate. These protons act as local top gates and attract electrons to the regions right underneath them, making these regions locally conductive. You can erase the structure that you wrote. You can create various junctions by applying negative bias voltage or modulate the voltage. And the best resolution that we can achieve is approximately 2 nanometers. So with this conductive lithography and the devices we created using it, we saw a lot of unforeseen observation for the superconductivity of strong-10 titanate. For example, in single electron transistor, we saw that electrons remain paired even after the superconductivity is destroyed by applied external magnetic field. In dissipationless electron waveguides, we saw that the electrons form multi-electron bound states from 2 electron pair, 3 electron trion, 4 electron quaternions, and so on, in a series of nanowires with varying width. We saw that the superconducting critical current does not scale as a function of the width. and therefore we concluded that the superconductivity for this heterointerface may be only exist along the edges. And the edges is highly likely to be ferroelastic domains. So what are those ferroelastic domains? We know strontium titanate has a structural transition at 105 Kelvin. And that structural transition is due to the antiphase rotation of the oxygen octahedra for strontium titanate. And this structural transition allows strontium titanate form X, Y, or Z domain. And these X, Y, Z domains has been observed under many different experimental techniques. Notably, for example, scanning single electron transistor, scanning squid, and so on. And these domains are found to have profound impact on the property of the transport of strontium titanate. It modulates the current density, it modulates the superconducting transition temperature. So there, we propose that the superconductivity of strontium titanate maybe only exist at the domain walls of those structured domains. And maybe that the ferroelastic domain wall is the mediator, the parent glue for the superconductivity of strontium titanate. So here we look at a similar case. Just 2 nanowires, a straight nanowire and zigzag nanowire. And the path length for the straight nanowire is 5 microns, zigzag nanowire 10 microns. So before seeing the data, I naively thought that because the zigzag nanowire is longer in path length, so therefore I will assume that normally the normal state resistance for the zigzag should be larger. And furthermore, the zigzag nanowire has these additional sharp turns that perhaps these sharp turns would promote the probability of having facelift centers, and therefore making the superconducting state's residual resistance higher in the zigzag nanowire. And here is what we saw. The IV curve for the straight nanowire and IV curve for zigzag nanowire. And this is completely opposite to what we previously expected. For example, the zigzag nanowire has larger critical current, lower residual resistance, and normal state resistance. And we repeat overall 23 devices. Some of the devices are within the same canvas and same cooldown, and some of the devices are not. And if we plot the distribution of the residual resistance as a function of number of sharp turns, and this is the overall scatter distribution. And so we can sort of see a weak trend that the residual resistance decreases as the number of sharp turns increases. And the trend is weak, but it's more apparent if we only look at the longer devices. So how do we explain this? We try to employ a phase field modeling for strontium titanate. So to do that, you track the relevant order parameters for strontium titanate. Here we have polarization order parameter P and antiferrodistortive order parameter Q. And you allow the system to evolve, you specify some initial condition, and you got final order parameter after thousands of, or tens of thousands of evolution steps, and then you obtain final domain morphology. So if there's no any charge distribution and no applied exchange and so on, then this is what we got for strontium titanate at 40 kelvins. Mostly X and Y and Z domains, which is what we expect. On the other hand, if we specify certain charge distribution, this 3D rectangular region. And then we allow the system to evolve. This is what we got. So we see that the highlighted region, the region that's encircled by the dashed line, is the region that's occupied by charge. And we see that the region occupied by charge is majorly C plus or C minus domains. And these C plus and C minus domains are the Z domains that we caught earlier. And right outside the Z domain, we have Y domains, which is the A2 plus and A2 minus here. And this picture having a nanowire running along the x-axis, and this nanowire sees a YZY domain pattern, is exactly consistent with the picture that we proposed previously. On the other hand, if we look at the temperature dependence, we see these domains only start to form for a temperature below 105 Kelvin, which is consistent with the critical temperature for the structural domains to form. Now, and we can also see that without charge distribution, that the domain for morphology is completely different. So now the question is, how different would a domain morphology seized by a zigzag nanowire? So this is the domain morphology from a straight nanowire, and this is the domain morphology from a zigzag charge distribution. And so here we see that even though that originally in the straight nanowire, we have this domain wall between C plus and C minus. On the other hand, the zigzag nanowire is occupied by a continuous C plus domain. So even though this may be too early to draw any conclusion, but there's a possibility that the straight nanowire has larger residual resistance and normal state resistance for the devices that were observed. So, and these are head to tail domain walls, hard domain walls. And these hard domain walls are predicted to be polar. So to wrap up, that we saw that the interplay between charge ferroelastic degree of freedom for SrTiO3 tightening can cause unexpected low resistance states in nanowires. And we believe that understanding the domain wall and the domains for SrTiO3 tightening is a key to understand the superconducting mechanism. And so thank you for your attention.